Hello and welcome to the Chemistry Solution. This tutorial is on electronegativity and bond polarity. When we draw Lewis structures, we draw the bonded electrons as a line between two atoms, and these electrons are visualized as being shared equally between those two atoms. But most of the time, electrons are not shared equally between two atoms. This is only the case with two identical atoms. Oftentimes, electrons are shared unequally, and that's because different elements differ in their electronegativities, or their tendency to attract electrons in a bond towards them. The more electronegative an atom is, the greater pull that atom will have on the shared electrons in a bond. And so normally, when you start talking about bonding, you talk about ionic bonds, where electrons are essentially transferred from one atom to another, and you talk about covalent bonds, where electrons are shared between two atoms. And we're going to expand on the definition of a covalent bond today. So in a non-polar covalent bond, that's where you have electrons shared equally. But there's also such a thing as a polar covalent bond, and this is where you have electrons shared unequally. And so the type of bond you have can theoretically fall anywhere in this range. It can be completely non-polar covalent when you have two identical atoms, where you have electrons shared equally, varying degrees of electrons being shared unequally, all the way through having electrons transferred from one atom to another, in which case you would have an ionic bond. So for example, in the molecule Cl2, the bond between the two chlorine atoms is a nonpolar covalent bond. Because both of the atoms are identical, each atom has the same electronegativity, or the same pull on electrons shared in a bond. In a polar covalent bond, such as the bond between HF, the electrons are shared unequally. Fluorine, being the more electronegative atom, has a much greater pull on the electrons in the hydrogen-fluorine bond than hydrogen does. Where potassium chloride is an example of an ionic bond, where essentially the electron from potassium is transferred to chlorine, forming two ions. When you have a polar covalent bond, you can designate partial positive and partial negative charges using the Greek symbol delta. And so because fluorine has a greater pull on the electrons in the hydrogen-fluorine bond than hydrogen does, those electrons will be near fluorine more often than they would be near hydrogen. And this gives fluorine a partial negative charge. And because the electron wasn't transferred from hydrogen to fluorine, fluorine doesn't have a complete negative charge like in the example of KCl, but those electrons will be more often around the fluorine atom than hydrogen, and so fluorine has what we call a partial negative charge, and this leaves the hydrogen atom with a partial positive charge. So like I mentioned before, bond polarity is due to a difference in electronegativity of two atoms in a bond. And electronegativity is the tendency of an atom in a bond to attract the electrons to itself. And we can gauge how electronegative an atom is using our periodic table. And as you move from left to right across the periodic table, the electronegativity of atoms increases. It also increases as you move from the bottom of the periodic table to the top, with the main exception being the noble gases. This makes fluorine the most electronegative element on the periodic table. Something that's really important to remember is that electronegativity is not the same as electron affinity. So remember, electronegativity has to do with atoms in a bond, and it's the tendency of an atom in a bond to attract the electrons in that bond to itself. Electron affinity, remember, is the energy change associated with an atom gaining an electron. And so although electronegativity and electron affinity have the same general periodic trend, remember that these are two different things.
Let's look at an example. Arrange these bonds in order from least to most polar. A fluorine-fluorine bond, a silicon-fluorine bond, a nitrogen-fluorine bond, and an oxygen-fluorine bond. Remember that electronegativity increases as you go from left to right across the periodic table and also increases as you go from the bottom to the top of the periodic table. And the polarity of a bond increases as the difference in electronegativity between the atoms increases. So there's a couple of different ways you can do this problem. If you have a periodic table that lists electronegativity values, you can calculate the difference in electronegativity between the two atoms in the bond and then arrange the bonds in order from least to most polar. So the smallest difference in electronegativity to the largest difference in electronegativity. Most of the time, what you're going to be doing is just looking at your periodic table with no electronegativity values and trying to estimate which bond is going to be the least polar and which bond is going to be the most polar. So in this example, I'm going to show you how to arrange these bonds in order from least to most polar, following the general trend for electronegativity on the periodic table and not using actual electronegativity values. So in general, for the most polar bond, you're going to look for the atoms that are the furthest apart on the periodic table. And the opposite is also true. For the least polar bond, you're going to look for the two elements that are closest together on the periodic table. In this example, your least polar bond is going to be a fluorine-fluorine bond. Whenever you have two atoms of the same element bonded together, the difference in electronegativity will always be 0. So this is an example of a non-polar bond. Following the general trend that the polarity of a bond increases as atoms of an element get further apart on the periodic table, the least polar bond after the fluorine-fluorine bond would be the oxygen-fluorine bond. As elements get further apart on the periodic table, the bonds tend to get more and more polar. So the nitrogen-fluorine bond would be the next most polar bond. And the most polar bond out of the examples that I've listed in this problem would be the silicon-fluorine bond, because these two elements are the furthest apart from each other on the periodic table. Thanks for watching the chemistry solution. We hope you enjoyed this tutorial.